the probability of getting an x-coordinate, so the probability of getting x in a small width dx is shown by this orange rectangle, or actually it's the purple inside this orange rectangle. So here, let me just be clear when I write dx, say x is in dx, dx has a double meaning here. Dx means a small width around a point x, as I've drawn here, as well as a width dx. So x is in this small width just to the left of x with width dx. That's what that means. And so if you wanted to approximate this area, it's obviously close to f of x dx, the area of the rectangle in orange here. So dx here, as I just said, is a tiny interval around x and also the length of the interval. So if you want to find the probability that x is between a and b, then you would write, this is the integral for x between a and b of the probability that x is in dx. So the probability that x is in dx is approximately f of x dx, and that approximation gets closer and closer the smaller that dx becomes, as you're familiar from calculus. So note that f of x is not a probability. F of x dx is a probability. F of x is actually having units probability per unit length. And another thing to note is that the probability that x is any particular value is 0. You can think that it's highly unlikely that if out of a continuum of values that you're going to get exactly that one. And or you could think of x equals x as being a rectangle with no width, hence no area. So a consequence of this is that the probability that x is between a and b, including endpoints, is the same as the probability that x is between a and b, where here we have a strict inequality. So really you don't have to worry about endpoints, and I often won't. So here's a problem where we randomly throw darts at this triangle. Now this triangle is not a density because area is 1/2 height times width, and so you can see that the area of this triangle is 3. So to convert it to a density, well, x needs to take values between -2 and 1, and so we can't change that. What will change is the height. The height of this triangle you can lower to by 1/3 so that the area will be 1. So we'll change that vertex from 0,2 to 0, 2/3. And to find the probability that x is in dx, for the x shown in this picture here, so now the height is going to be x plus 2 over 3, and the width is dx. And we can write the density for the 3 regions, the region between -2 and 0, between 0 and 1, and outside of -2 to 1. So now expectation has a similar definition to in the discrete case. So I'm going to assume that infinite sums converge, and so I'm going to replace my summation with an integral, and I'm going to replace the probability that x is x with the probability that x is in dx. Probability that x is in dx can be approximated by f of x dx, and so that is our definition of expectation of a function. So, for example, expectation of x and expectation of x squared then follow these formulas, and the variance of x can then be determined from our usual second moment minus the first moment squared. So, for the standard uniform, this has density that looks like a square, and the expectation of u here is 1/2, as makes sense in this picture, and the expectation of u squared, so that's the integral from 0 to 1 of x squared dx, because again the density is 1, so that's 1/3, and the variance is 1/3 minus 1/4, which is 1/12. So we can use this. We can use this facts, for example, to find the expectation and variance of more complicated uniforms, and we'll do that a little bit later. But I need to introduce change of scale. So to calculate the expectation of x, the variance of x, the probability that x is in dx, we sometimes make a change of scale. Y is c plus dx, where c and d are constants. So y, so the purpose for doing this is that y will have a simpler density than x does. And we can easily recover the expectation of x, or the variance of x, so we can recover these from the expectation of y, the variance of y, and to see that, just notice that, let's see here, so let's do variance. So the variance of y, so for example, the variance of y is the variance of c plus dx, and that's just the c dies. So the c just dies, and the d pulls out as a square, so we get the variance of x. So that means that the variance of x is the variance of y over d squared. Okay, and so you can similarly get expectation, and we'll look at some more examples here. So for example, let's say that x is normal mu sigma squared, and you want to find the probability that x is between 1 and 2. So I want to find this area shown here. So let's make a change of scale. So we're gonna make a change of scale so that mu gets shifted to 0, and sigma will become 1. In other words, we're going to make our normal curve into the standard normal curve. So our change of scale is just going to be x minus mu over sigma, and I'm dividing by sigma here, not sigma squared, because I want the variance of z to be 1. So I can show you here. So note that the variance of z is the variance of minus mu over sigma plus 1 over sigma x, which is, now 1 over sigma pulls out as a square, variance x, which is just sigma squared over sigma squared, which is 1. So that's why we divide by sigma, not sigma squared. Okay, great. So I have this change of scale. I can solve for x in terms of z very easily. And so to find the probability that x is between 1 and 2, I'll just substitute that x in here. And then I see that that's the probability that z is between these two values. And I can just use the CDF of the standard normal, which is capital Phi here, to find that. So I asked you, say that x is uniform AB, which has density 1 over b minus a for x between a and b. So I asked you to find a change of scale so that you can easily find the expectation of x and the variance of x. So the obvious change of scale is we want to convert this to the standard uniform. So u will be x minus a. I'm transferring a to the origin, and I'm dividing by b minus a. And so that is a change of scale. The expectation is easy to find, and you then get, because you're using the fact that the expectation of u is a half, and the variance is easy to find because we know the variance of u is 1/12 from earlier. So you can easily find formulas for expectation of x and variance of x. So we ended with a concept test here where suppose that suppose a manufacturing process designed to produce rods of length 1 inch exactly, in fact, produces rods with length distributed according to the density graphed below. So you should change the scale x, which is the length of the rods, to which of the following. So x taking values between 0.9 and 1.1, it'll be much more convenient for x to take values between -1 and 1, so that the average is 0 instead of 1. So we're going to make a change of scale here. And so to shift 0.9, to shift the interval 0.9 to 1.1 to -1 to 1, we shift x by 1, we translate, so we have x minus 1, which will move the it'll move the 1 to 0, and it'll move the 0.9 to -0.1, and then we need to multiply it by 10 so that -0.1 becomes -1. So now this will make, so the density of y now, for it to be a density, we know what height our triangle needs to be. And that height is 1 because the area needs to be 1, and so it can't be anything else. So we get the height, once we make our change of scale, we know what height to make our triangle because it has to have area 1. So none of the answers fit except D, so the answer is none of the above. And once you make this change of scale, now the density for y is really easy to write down. It's just minus y plus 1 when y is between 0 and 1, y plus 1 when y is between -1 and 0 otherwise, and it'll be easy to make calculations with this density. Then and from that we'll figure out things that we're desiring to know about x, and we'll look at this next time. Have a great day.